All right, today we're going to uncover the secret chemical journey that takes us all the way from a drop of crude oil to the Teflon pan sitting in your kitchen. It's an incredible story of breaking things down just to build something even more amazing. I mean, think about it. It seems kind of crazy, right? One carries water, the other cooks your breakfast. But believe it or not, they share a common ancestor, a super simple molecule that goes through an incredible transformation. So let's dig in and see how this all works. Every great story has a beginning. And for the plastics and materials that pretty much shape our entire world, that story starts deep underground with these really simple molecules called hydrocarbons. The raw stuff we're starting with, it's called alkanes. Now, these are the absolute backbone of organic chemistry, just simple, stable chains of carbon and hydrogen atoms. We pull them from the earth as petroleum and natural gas, and they are our starting point for everything else. You're actually surrounded by alkanes. You just might not know it. The natural gas heating your home? That's mostly methane, the simplest alkane there is. The butane in your lighter? Yep, an alkane. The propane you use for the barbecue? You guessed it, another alkane. They're fantastic as fuels for sure, but their real power, the ability to build with them, well, that only gets unlocked when we figure out how to take them apart. The thing is, in their natural, long-chain form, they're not very useful for building stuff. So the first thing we've got to do is a little bit of what I like to call creative destruction. We need to smash them into smaller, more versatile pieces. And the name for this process is just perfect. It's called cracking, because that's literally what we do. We apply intense heat and cause those long alkane chains to crack apart into smaller, much more useful molecules. Okay, imagine you have a long piece of uncooked spaghetti. Snapping it into smaller bits makes it much easier to work with, right? That is basically what we're doing here on a molecular level. We start with a long alkane, hit it with heat, and create these smaller pieces called alkenes. Now, alkenes are special. They have a bond that makes them super reactive. They're just dying to link up with other molecules, which makes them the perfect building blocks. All right, so we've done the breaking part. We've got our big pile of chemical Legos. Now comes the really fun part. We get to build something totally new. And to get this, you just need to know two key terms, monomer and polymer. A monomer? That's your single Lego brick. It's one of those little reactive alkene molecules we just made. A polymer is what you get when you snap thousands of those Lego bricks together to build your final masterpiece. And the magic that snaps all those bricks together? It's a process called polymerization. It's this amazing chemical reaction that forges super strong links between all those individual monomers, creating one long, stable, repeating chain. This, right here, is where simple gas molecules get turned into strong, useful materials. So, what kind of incredible stuff can we actually build this way? You're going to recognize a few of these for sure. Let's take a look at the Polymer Hall of Fame. So first up, we have this one. Get ready for it. Polyvinyl chloride. Yeah, I know, sounds like something you'd only hear in a chemistry class, right? But I bet you know it by its initials, PVC. Yep, that stuff. It is absolutely everywhere. So by taking a monomer called vinyl chloride and just chaining them all together, we get this incredibly useful material. You need something lightweight but also really tough and long-lasting? PVC. Something waterproof that you can mold into any shape? PVC again. It's why it's perfect for everything from the pipes in your walls to the casing on your computer. All right, you ready for another one? This one is a real mouthful, I'm not gonna lie. Polytetrafluoroethylene. But, trust me, this one has completely changed how we do things in the kitchen. You know it much better as Teflon. That's right, the non-stick magic that makes your morning eggs slide right out of the pan without a fight. That super slick coating is just another polymer, made by linking up a whole bunch of tetrafluoroethylene monomers. So, remember our question from the beginning? Your water pipe and your frying pan? Well, there's your answer. They are both polymers, born from the exact same chemical playbook. But, sometimes just making the polymer chain isn't quite enough. Sometimes the finished product needs a little extra help to be truly useful. And a perfect example of this is natural rubber. In its raw form, it's got some big problems. Yeah, in its raw state, it's basically a sticky substance with low elasticity. That is not the durable, bouncy stuff we need for things like tires or the soles of our shoes. It really needed a chemical upgrade. And that upgrade came from Charles Goodyear in a process called vulcanization. What he figured out was, if you heat natural rubber with sulfur, something amazing happens. The sulfur atoms form these little bridges between the long polymer chains, locking them all together. And that simple trick transforms that sticky mess into the hard, durable, elastic rubber that we know today. And what's really wild is how much the amount of sulfur matters. It completely changes the final product. Add just a little bit, say 1 to 5%, and you get soft, flexible rubber. Think shoe soles or rubber gloves. But crank that sulfur content way up to 30 or even 50%, and you create the incredibly hard rubber you need for car tires, all by tweaking one ingredient.
Okay, so let's zoom out and pull all these threads together. We've seen how we can take these simple molecules, break them apart, and then rechain them into totally new materials with all these incredible properties.
This whole invisible dance of chemistry, the cracking of long chains and the polymerizing of short ones, is the hidden architect of our modern world. Seriously, from our homes to our kitchens to our cars, these materials that all started as crude oil are absolutely everywhere. So from a simple hydrocarbon, through this process of breaking and linking, we've built a world of plastics, rubbers, and fibers that define modern life. It's pretty amazing when you think about it. And it leaves you with a really big question. Now that we know how to do this, what new materials are still just waiting to be chained together? What are we going to build with them next?